So at the end of the last video, I accidentally hit stop as the phone was ringing instead of pause, and so this is now a new video to continue what we were saying. Nonetheless, so mathematicians have defined 0 factorial to be 1 so that we can follow this pattern here. One other thing to note, we're using the notation that the nth derivative is represented this way. So with that in mind, and to follow the pattern, we're going to call the 0th derivative just f. So it sticks with the notation as well. All right, so let's state this as a theorem and give it its formal name, as I've already used the name, but we'll state this as a theorem. And in fact, I'm going to pause the video to write this out so you don't have to listen to me write and talk. It's a long theorem, so get ready. You may need to pause it because I may scroll too quickly. But it says if f has a power series representation at x equals a, that is if f of x is equal to c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared, and so forth. And then you can see in the summation notation. There's a little bit of a typo here. I don't know if I can fix that while you guys are copying here. I need to move this over. And nope, that didn't work. I'll try that again. Let's try this. Yeah, because I need a plus dot 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 in here. This goes on forever. For the absolute value of x minus a less than r, that's the power series for f, then its coefficients are given by the formula. So each of those c sub 0, c sub 1, all the way up to c sub n, and so forth, is going to be the nth derivative. Okay, so we say this in this way here. The nth derivative of f at a divided by n factorial. The nth derivative of f at a divided by n factorial. All right, so that's how we will find all those coefficients. And again, this is kind of a long theorem. Then f of x would be equal to, and this is just how we would write this out. So I'm now putting in the value of each coefficient. As we said earlier, c sub 0 is f of a. So f of a plus f prime of a over 1 factorial times the quantity x minus a plus f double prime of a over 2 factorial times x minus a squared. And that pattern just continues. Whatever derivative we're taking of f, we're going to evaluate that at a and divide that by that number derivative factorial. So f triple prime, the third derivative of f at a, divided by 3 factorial. And then we're going to multiply by x minus a quantity cubed. All the way out to the nth. The nth derivative of f at a divided by n factorial times x minus a to the nth power, and so forth, plus dot dot dot. And then if you want to write that in summation notation, it's the sum from n equals 0 to infinity, the nth derivative of f at a divided by n factorial times x minus the quantity x minus a to the nth power. And this is called the Taylor series of f at x equals a. I don't like that line came out. So the Taylor series of f at x equals a, or centered at a. So that's what a Taylor series is. Okay, this is what it is. It's the power series for some function f, where it's and this is how you generate all of those coefficients. Let me scroll up and give you the last part of the theorem. Again, pause it as needed. If we allow a to be 0, then f of x is going to be, instead of f of a, it's going to be f of 0 plus f prime of 0 over 1 factorial times x. It's no longer times x minus a because a is 0, so x minus 0 is still x. Well, I mean, it still is x minus a, but it's simplified to x. Plus f double prime of 0 divided by 2 factorial times x squared plus f triple prime of 0 divided by 3 factorial times x cubed, and so forth. To get to the nth derivative of f at 0 divided by n factorial times x to the n, or you can write that in summation notation. This is called the Maclaurin series of f. Now, hopefully you recognize that a Maclaurin series is just a Taylor series with A equal to 0. Okay, so a Taylor series is a little bit more general than the Maclaurin series because the Taylor series can be centered anywhere, and the Maclaurin series is just centered at 0. So a Maclaurin series is a Taylor series with the center A equal to 0. On the AP exam, they sometimes will ask for the Maclaurin series, and then they will sometimes ask for the Taylor series centered at 0, which is just the Maclaurin series. And I don't know why they do that, but they have asked that questions like that in the past. So just be ready. So they could ask you for the Taylor series centered at some number other than 0. They could ask for the Maclaurin series, which means the Taylor series centered at 0, or they might use the phrase generate the Taylor series centered at 0 for some particular function. All of those things are possibilities. It seems like a lot to remember, but as human beings, we're pattern recognizers and utilizers, and so you want to just absorb the pattern that we see here because it's just a pattern, and if you can just absorb the pattern, you'll be able to remember it. It's not there might be a lot of symbols involved, but it's not that complicated, and you certainly can understand it and recall it. But you want to commit this to memory so you don't have to go back and look it up, and so that you can utilize it anytime you need it. Okay? We're going to look at some examples right now. So our first example is to find the Maclaurin series for sine of x, and we want to find the interval of convergence. So remember, a Maclaurin series is a Taylor series centered at 0. It's a power series, but we don't have the relationship between sine and some other function in order to generate the power series for sine using the techniques that we learned in section 8.6. And we want to practice this theorem anyways, this essentially a definition, so we can work this out. Now, to generate this Maclaurin series, all those words were right. I'm just going to use the one that I asked about. To find the Maclaurin series, I need to find those coefficients. I need to find C sub 0, C sub 1, C sub 2, and so forth. So let's start making a list here a little bit. Now, f of x is going to be equal to sine of x. We know that. We were given that. And so f of 0, well, sine of 0 is 0. Okay. Now remember, that's going to be C sub 1. All right. Now how do I get... I'm sorry, C sub 0. That's going to be C sub 0. How do I get C sub 1? Well, I need f prime of x. F prime of x is cosine of x. So f prime of 0, well, cosine of 0 is 1. So that's going to be 1. And that means C sub 1 is going to be 1 divided by 1 factorial, which is just 1. Well, going back up here for just a moment, that means C sub 0 is going to be 0. Now, if I continue, f double prime of x is going to be negative sine of x, and f double prime of 0 is going to be 0. Okay, so that tells us C sub 2 is going to be 0. I don't need to divide 0 by 2 factorial to know that's going to be 0. But if you want to write that over 2 factorial in your notes, you can. What about f triple prime of x? Well, f triple prime of x is going to be negative cosine of x, and f triple prime of 0 is going to be negative 1, which is going to tell us that C sub 3 is going to be negative 1 over 3 factorial. Feel free to work faster than I am. So the fourth derivative of x, well, we're back to sine again. And the fourth derivative at 0 is going to be back to being 0 again. It tells me C sub 4 is going to be 0 again. And we've dealt with these types of things before, patterns for the derivatives of sine and its evaluation, or cosine. So notice that all of the coefficients with an even subscript, 0, 2, and 4, all become 0, and that's going to continue. And all those with an odd subscript are going to be either, well, the derivatives are going to be 1, and then negative 1, and then 1, and then negative 1. And then the coefficients are going to be that 1 or negative 1 divided by whichever factorial we need to divide by. So this should be pretty straightforward for writing out the Maclaurin series here. So f of x is equal to sine of x, which is equal to, let's be really deliberate here for a moment, and then we will be less deliberate in future examples. 0. Okay, that's c sub 0, or f of 0, which is in the definition, plus 1, yeah, 1 over 1 factorial, I'll put it down there, times x to the first power, plus 0, let's put that over 2 factorial now just to follow the pattern, times x squared, plus, actually, yeah, I'll put a plus, negative 1 over 3 factorial x cubed, plus 0 over 4 factorial x to the fourth. I'm tired of writing this out already. Let's go ahead and start simplifying, and then we'll write the nth term in just a moment. So sine of x, it's Maclaurin series. This is just x minus 1 over 3 factorial x cubed plus, because positive 1, negative 1, positive 1, 1 over 5 factorial x to the fifth, minus 1 over 7 factorial x to the seventh, plus dot, 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 plus. All right, now we got to figure out here. So we're alternating. So we're going to have negative 1 to some power, perhaps to the nth power. I'll put it there, but I reserve the right to change it later if I see fit. And then we're going to have x to some power. And what's that power? Notice they're always odd numbers. So how do we write an odd number? Well, an odd number is always an even number plus or minus 1. I'm going to use a plus 1. You could use a minus if you want. So an even number is 2n, so 2n plus 1 will always be odd. And then notice that, the same factorial is the exponent that we have here. So this is going to be 2n plus 1 factorial in the denominator. And make sure you have parentheses around the 2n plus 1, otherwise the factorial is not applied to the whole expression properly. And then plus dot, dot, dot. And there's our Maclaurin series for sine. So let's take a look. I want to show you guys what the graph of this looks like here for different numbers of terms, okay? So similar to what you did in an earlier activity, well, assuming I assign that to the group that I'm talking to at the moment, but nonetheless. So what do I have? I have sine of x in red, as you can see, and then I have the series here, but I have it stopping at values of I. So this is not the infinite series. This is not the whole sum. This is in this case, the ith partial sum. And right now I is 0. So this is literally just the very first term. The very first term was x, okay? And so this is just y equals x. And there's the first term, okay? I don't want to comment too much just yet. Let's move it over. Now if I let I go to 1, and now we have x minus 1 over 3 factorial times x cubed, I get this. Now notice that the graph looks pretty good, close to 0 at least. The first two terms do a pretty good job of approximating the curve really close to 0, really close to the center. Now we get to 2, so now we're at the 5th degree polynomial, which looks like this. And then so forth on down the line. I'm just going to keep adding more terms here. And as I add more terms, you can see that the curve is being traced out here for a larger and larger interval. Still centered at 0. We have nice symmetry happening here. And I'm going to stop at 20 terms right over here. And it doesn't quite get the whole screen, but that's okay. I wasn't intending for that. I could add more terms. I can make that 20 a 50, and I'll certainly get beyond the domain shown in the screen. But, that's a pretty cool picture, in my opinion. And I hope you can see, the power of this Taylor series here, this Maclaurin series, as it's giving us a better and better approximation for the curve with using more and more terms. There's one more cool picture that I want to show you. Instead of just doing the 20, the first 20 terms like I had before, which did a really good job, I'm going to plot each partial sum, one term, two terms, three terms, up to 20 terms altogether, and check it out if it pops up. There it is. These are all of them, except for the very first term, the single term by itself. I left off from my list accidentally the single term, just x. But other than that, what I love about this graph is if you put all of these together here, you can see the sine graph formed in the overlap from these different expressions. To me, that's a really cool representation of the Taylor series here, or the Maclaurin series for sine of x. So that's really cool. Now, what we haven't done yet is we haven't done the second part of the question. We haven't found the interval of convergence yet. But I want to pause on that one more time. Let's get rid of this. Let's go back up here, and let's go to the very first term for the Maclaurin series. If I just type x, what do you notice about that? Hopefully you notice that that's the tangent line to the curve right there. If I just go back to the AB class and I take, the derivative, f prime of x equal to cosine of f. The center in this case is the point of tangent line, so f prime of 0 is going to be 1. And so the equation of the tangent line, if you go, way back to the AB class, y equals, f prime of, in this case, 0 times x minus 0 plus f of 0. That's just going to be 1 times x plus 0, or just x. I'm letting that sit for just a moment. That is so cool. If you've never seen that before, and you probably haven't, just let you appreciate that. Okay. If I just look at this, with just this term only right here, then I'm using the tangent line. So you can interpret this here. Oh, I don't know what just happened there. Something just rebelled on me, but nonetheless, if I look at these two terms here and just plot those two terms, this could be considered like a tangent. I'm putting quotes around the word tangent, but a tangent cubic. Instead of a tangent line, it's like a tangent cubic. Okay, and if we go back to the graph over here and we get that tangent cubic here, what are we seeing right here? We're seeing that the cubic does a really good job of approximating the outputs of the function near the center, near the point of tangency, quote in quotes here, which is how we look. That was our local linearity property from tangent lines. They do a really good job of approximating the curve near the point of tangency. And when you zoom in, they're indistinguishable. If I zoom in, whoops, I got to zoom in properly here. If you zoom in, you can't even tell them apart. And so we have a tangent cubic, if you will. Again, tangent in quotes, or tangent quintic, fifth degree, septic, and so forth on down the line. What we're doing here with the, I don't know what just happened with the jump, with the Maclaurin series here, or a Taylor series, is we're generalizing the concept of a tangent line to higher degree polynomials. This is a lot more powerful than just using a tangent line, because a tangent line, if the graph curves, and then as soon as there's some curving of the graph, then the tangent line is no longer helping us generate approximations to the curve, or at least not reliable ones. But if you can use a cubic, the cubic's going to curve too, and it's going to hopefully match a bit of the curvature of the function for a little while and give you a wider interval on which the approximations are valid. And same with the fifth degree, and same with the seventh degree in this. So the more terms you use, you're using a more general tangent curve to the function that gives us better and better approximations to the function over wider intervals. Now, come on, that's cool. You have to like that one. All right, let's do the last part of the question. That's to find the interval of convergence. And so we're going to use our ratio test. So we're going to take the limit as n approaches infinity, and we need the nth term. Now, the nth term had -1 to the n in it. You know what? I didn't comment on that, so let me comment really quickly. Up here, in order to generate the 2n plus 1, or rather to use the 2n plus 1 to generate the terms of the series, I have to start n at 0. So if n equals 0, then this becomes x to the first power, which is my first term here. And this is going to be positive, so positive, divided by 1 factorial, which is still 1. So I'm using starting at n equals 0 to plug in to generate the terms of the series. If I plug in 1, then I'm going to get x cubed over 3 factorial, and this becomes negative, and so that's how the terms are formed. But nonetheless, let me keep that on the screen here. I don't need to put the -1 to the n in the absolute value because the absolute value is going to get rid of that. But I need to increment n to n plus 1. So 2 times the quantity n plus 1 plus 1 over, and then same thing here in the expression in the denominator, like this, and then multiply by the reciprocal, 2n plus 1 factorial over x to the 2n plus 1, like this. And let's see what happens here. So how are things going to cancel? Well, let's do some simplifying first to make sure we can see the patterns that are going to come out. So the limit as n approaches infinity. We're going to get x, well, we still have our absolute value. Now 2n plus 1 times 2, or rather, n plus 1 times 2 is going to be 2n plus 2 plus 1 is going to be 2n plus 3. And then this is going to be 2n plus 3 factorial. And we still have our 2n plus 1 factorial here, and then x to the 2n plus 1. So what in fact cancels here? Well, with these two things, you just got to subtract the exponents, and those exponents are 2 units apart. So we're left with an x squared up here. 2n plus 3 minus the quantity 2n plus 1. The 2n's are going to cancel. 3 minus 1 is 2, so I have a 2 left in the exponent, or x squared. Now, the cancellation here hopefully is not too challenging to see, but if I start to write this out, starting from the highest number down to the lowest, I would have 2n plus 3 times, well, I got to subtract 1, 2n plus 2 times 2n plus 1 times 2n. Well, anything after that's just going to be 2n plus 1 factorial. So that means I can cancel all of this with all of this, and I'm left with these two expressions in the denominator. So this works out to be the limit as n approaches infinity. We have our absolute value of the quantity x squared in the numerator, the quantity 2n plus 3 times 2n plus 2 in the denominator. Now remember, as n goes to infinity, x is a constant. So x squared in the numerator here is a constant, and that constant is being divided by larger and larger numbers, because both of these expressions here are going to get bigger, and the product gets bigger at an even faster rate. And so this is going off towards infinity, larger and larger numbers, growing without bound, constant here in the numerator. So this, regardless of what x is, this will always have a limit of 0. Now, by our ratio test, that's good. That means we get what we want. In other words, 0 is less than 1, and when that limit from the ratio test is a value less than 1, then the series will be absolutely convergent. And now this is telling us that the series is absolutely convergent no matter what value we plug in for x. And so that means the interval of convergence here is going to be -infinity to infinity, or all real numbers. If we go back to that graph that I was doing, back over here, and getting wider and wider values. If I just zoom out, oh, that's not very. Oh, okay, there it goes. I was going to say, why did it stop? I think my computer just couldn't keep up with it. This should go on forever. There it goes, starting to fill in. Now, the blue graph obviously stops at a certain point because I only got 20 terms, but if I was to change the 20 to some larger value, let's say 50 over here, like this, and then what's going on? I drag that over to 50. Eventually, my computer will catch up and gives me a wider interval of convergence. I would expect it to be better than that. That's looking a little better. My computer's still acting a little bit funny at the moment. That's not how it should look. I bet if we just wait a moment, it'll look better. Hopefully, if not, you can go type this in yourself into your own Desmos browser, and then see how it's gonna work out. I'm gonna make it a little smaller I don't know what's going on, but anyway, as long as I use enough terms, we can go out to negative infinity to infinity. We can get to all values. Starting to catch up a little bit here. We're not restricted in any way. This Maclaurin series will be valid for all values of x. We just need to use enough terms to make it valid, and it's still acting a little bit funky. All right, I'm going to stop this portion of the video here, and we'll do other portions in subsequent videos. Go study.